Alright, we're going to be looking at Chapter 6, and we just briefly started looking at binary relations. In particular, we looked at 3 different ways that we could represent a binary relation as a set of ordered pairs, using an arrow diagram, or using a matrix. Okay. So, we want to look at a binary relation on a single set. So in this previous example for the binary relations, we had one set, 2, 3, 5, 7, and another set, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, these sets were different, and we had a relation that went from set A to set B, two completely different sets. Okay, so, but if we talk about a binary relation on a single set, instead of having 2 different sets, A and B, we're going to have the same set. Okay, so a binary relation on a set A is going to be a subset of a single set A crossed with itself. Okay, and then that set A is just called the domain of the binary relation. And then in an arrow diagram on a single set, really, it doesn't make any sense to take A and list, like normally when we do a relation, we would take all the things in the first set and all the elements in the second set and draw arrows between them for the relations. But if these and these are the same thing, okay, there's really no need to list them twice. So if we just have a single set, we're just going to list all of the elements one time, and then just draw an arrow from an element to another element if they are related. And this will produce something called a directed graph. Let's just do an example and we can see what a directed graph is. We'll define that formally in the next section. Alright, so let's say we had a relation from A to itself, okay, and A is the elements 2, 3, 4, and 5. So if it's going from A to itself, we're not going to list the numbers 2, 3, 4, and 5 in 2 separate groups. We're just going to list them once. So maybe I'll list them like 2, 3, 4, and 5. And they don't need to be in a straight row or anything. In fact, that might make it even harder to be able to follow all the arrows if they're all lined up in a row. So you might want to just kind of group them in a circle. Okay, now we can see that A is related to B if 2 divides the product AB. Okay, so we might ask ourselves, alright, is 2 related to itself? Well, 2 is related to 2 if 2 divides the product of 2 times 2. Certainly 2 divides 4, and so 2 is related to itself. Is 2 related to 3? Okay, well, 2 would be related to 3 if 2 divides the product 2 times 3. Certainly it does, because 2 is one of the factors. Okay, hopefully we can see that 2 is going to be related to everything, because 2 is going to divide 2 times anything. So 2 will be related to 3, it'll be related to 4, it'll be related to 5. And we go on to 3. Is 3 related to itself? Well, 3 would only be related to 3 if 2 divides 9, 2 doesn't divide 9, so 3 is not related to itself. Is 3 related to 4? Well, only if 2 divides the product of 3 and 4. Certainly 2 divides 12, so 2 is related to 4. Okay. When we multiply 3 and 5, 2 will not divide it, so 3 is not related to 5. Okay, is 4 related to 2? Yes. Okay, and 2 divides the product of 4 times 2. Is 4 related to 3? Yes. 2 divides the product of 4 and 3. Is 4 related to itself? Yes. 2 divides the product of 4 and 4. Is 4 related to 5? Yes, because 2 divides 4 times 5. Finally, is 5 related to 2? Yes, because 5 divides the product of 5 and 2. It's not related to 3 because 2 doesn't divide 15, but it is related to 4 because 2 divides 20. But the arrow diagram or digraph representing this relation would look like. Okay, so one interesting thing to notice on this is that if an element is related to itself, it's indicated by an edge or an arrow that's called a self loop. It loops back on itself. Okay, now if we had written these out, as 2, 3, 4, 5, 2, 3, 4, 5, and you would just see an arrow going from 2 to 2 or from 4 to 4. Since we're not listing them separately, it's just going to go back to itself. So this self loop right here represents that 2 is related to itself. This self loop right here represents that 4 is related to itself. There is no self loop at 3 or 5, which means 3 isn't related to itself and 5 isn't related to itself. Okay. All right, so let's say we've got this matrix below right here, and that represents a relation on a single set 1, 2, 3. So that is the domain of the relation. So let's look at how we could take that matrix and translate that into a set of ordered pairs and also as a digraph or arrow diagram for the relation. Okay, so we're going to take the elements of the domain 1, 2, 3, 4 and write them along both the rows and the columns because it's just a single set. And then remember, okay, if we see a 1, that means if we go from that row and that column, that means that 1 is related to 1. So if we're looking at a set of ordered pairs, okay, 1, 1 is one of the set of ordered pairs because 1 is related to 1. 1 is also related to 2 because there we see this first row, second column has a 1 in it, so 1 is related to 2. But 1 is not related to 3. Okay, 2 isn't related to 1, but 2 is related to 2. And 2 is also related to 3. And then 3 is only related to 1, but nothing else. Okay. So we have these. Notice that there are 1, 2, 3, 4, 5 ones, and there are 1, 2, 3, 4, 5 ordered pairs. The number of ordered pairs should match the number of ones that you see in the matrix. Okay. If we were going to draw the arrow diagram, we're only going to list the elements in the domain once. So maybe I'll put 1 and 2 and 3. Okay. And then 1 is related to itself, so I'll see a self loop there. 1 is related to 2, so there'll be an arrow from 1 to 2. 2 is related to itself, so I'll see a self loop there. 2 is related to 3, so I'll see an arrow from 2 to 3. And then 3 is related to 1. Okay. So if we count the number of these arrows that we see, there's 1, 2, 3, 4, 5 arrows. The number of arrows should match the number of ones that we see in the matrix. Okay, let's say we are given a digraph or arrow diagram and we want to come up with the ordered pairs and the matrix. So again, let's just go with the ordered pairs first. Okay, so we'll start with 1. What is 1 related to? 1 isn't related to itself. There's no arrow going out to 2, so it's not related to 2. But there is an arrow coming out towards 3 right here. That's 1 being related to 3. And there's an edge coming out towards 4. So we have that 1 is related to 4. I'm just going to check these off to make sure I get them all. So that's everything that 1 is related to. If we go on to 2, okay, 2 is related to 1. 2 is related to itself because of that self loop there. So I got that one, and then 2 is related to 3. And that seems to take care of everything from 2. Let's go to 3. So is 3 related to 1? Yes, it is. There's an arrow going back there. There's no edge going to 2, so it's not related to 2, but it is related to itself. And there is no edge going back to 4. And then if we go to 4, 4 is related to 1. There's an arrow going back there. It's not related to 2, is related to 3. Okay, and it's not related to itself. That should be everything. It looks like I've checked off everything, so the number of pairs in here should exactly match the number of arrows that we saw there. And then as far as the matrix representation goes, okay, we'll take the write it down for the rows and write it across for the columns. And that will, okay, and then we can just go through and fill in. So 1 was not related to itself. 1 was not related to 2. Okay, but it did go to 3 and to 4. And then 2 went back to 1. It was related to itself. It was related to 3, but not to 4. 3 was related to 1, not to 2. It is to 3, but not to 4. And then 4 is related to 1 and 3, but nothing else. Okay. So each of these are equivalent representations of the binary relation. Okay, so that should do it for section 6.1. And we'll cover 6.2 in a separate video.